So our next speaker is Vlad-Alexandru Silvestru. So Vlad is currently working as a researcher and lecturer at ETH Zurich. His research focuses on structural use of glass and on additive manufacturing applications for structural steel components. He'll be presenting an experimental study on using thermal treatment for stress relief in thermally tempered glass.
Thank you for the introduction. Today I will present an experimental study on using thermal treatment for stress relief in the context of reuse and remanufacturing. And in my presentation I will first give you a background for the reasons why we did this study, and then I will dive in the experimental study, focusing on all the different investigation steps, and finally give you some outlook on future steps. I would like to start with this slide showing different temperatures that are used in the production and processing of flat glass. Most of you probably know, are aware of these temperatures. For me, it was relevant to see what temperatures make sense for the heat treatment that I apply. And I would like just to point out maybe the 600 degrees at which the glass has sufficient self-stiffness when it comes out from the floating bath. The annealing point, which is quite relevant, especially if, in the tempering process, but also if we want to reverse this process. And what was also relevant for me is also the 290 degrees, which are used for commercial heat soak testing for fully tempered glass. Since at this temperature, it's expected that there is no reduction of the residual stresses, or only an insignificant one, I would say. I focus by using thermal treatment on two issues that are encountered with the condition state of dismantled aged glass. One of them are the scratches on the surfaces. We heard yesterday two interesting presentations on using heat treatment to heal such scratches. The second one, on which I will also focus more today, is maybe not at present now, because most of the glass that we retrieve nowadays is annealed glass, and the focus is mostly on annealed glass for reuse and remanufacturing. However, in the past years, we used more and more thermally tempered glasses, so I think that in the future, this might also be, there will be more tempered glass that we will retrieve from the buildings, and it might make sense to reuse it. Generally, you say that you cannot mechanically process it. At least since I started to deal with glass during my education, I always heard thermally tempered glass cannot be cut. In terms of reuse and remanufacturing, in my opinion, it's also about reversing processes. So I asked myself, could we reverse the tempering so we can also cut the glass? Of course, it's a matter of energy demand, so that has to be checked if it really makes sense. For the first topic, I will not focus a lot on it, but we also saw yesterday in the presentations that by applying different temperatures, we can heal to a certain extent the scratches. However, there are two aspects. One is increasing the strength of the glass that is scratched. The other one is the visual appearance. So the scratches might also disturb the aesthetics. And increasing the strength is already possible to a certain percentage with lower temperatures. But we saw also yesterday that the visible scratch might be still on the glass. So I thought, what would happen if we go higher with the temperature? And I just want to show you, this is at 700 degrees, so a temperature where the glass already loses a bit of the stiffness, but the crack actually is almost healed. So it was actually tough with the microscope to identify where the scratch previously was. And the strength that is achieved with this is actually similar to the non-scratched glass. And these were also, in my study, it was artificially damaged, but it could be applied also to naturally scratched, naturally aged glass. The problem is, by losing the stiffness, you need a substrate which is very flat, so you don't alter the the non-scratched surface. But this research is still in progress. Today, I would like to focus on the other issue, which is the stress relief. So the characteristic crack pattern of fully tempered glass is the one that you can see on the left. What we need mostly for cutting the glass is a crack pattern that is characteristic for annealed glass with larger fragments. So the question was, how can we get from this back to the initial annealed glass in order to basically be able to cut the glass? And for this, I conducted a study on different series. I used the glass panels 6 millimeter thick, fully tempered, with the sizes that are suggested in the EN 1288 part 3 for the 4-point bending tests. And I had some reference series without any heat treatment, a series where I heated it at 550 degrees, which is approximately the annealing point, for 2 hours. And then I also wanted to look what happens if I treat it at lower temperatures. So I chose 400 degrees, which is somewhere between the 550 and the 290 of the heat soak test. And here I also looked at different hold times, so 2 hours and 8 hours, to see what the difference is if we increase the hold time. However, I will show you that that's, in terms of energy consumption, that's maybe not that efficient. And the last series, the 2 panels, were treated also at 550 degrees, and I experimentally tried to cut them to see if also this is working afterwards. The study included measurements of residual stresses and geometry before treatment, thermal treatment in an electric furnace, again, measurements of the residual stresses and the geometry after the treatment, the 4-point bending tests, and for some samples, manual cutting of the glass. The furnace that we used is actually a furnace dedicated for fusing glass, so it's not optimized for this process, but it's the one that we had in the lab, and for the experimental study, it worked quite well. One of the concerns that I have is that the heating elements are on the ceiling of the furnace, and also the thermocouple for controlling the operation of the furnace is near the heating elements. So to be sure what temperatures I reach near the glass panels, I used some additional thermocouples to monitor the temperature development in this vicinity. And you can see here that actually the temperatures around the glass panels lagged a little bit behind the target temperature, which is the black curve in these graphs. So for the heating, I had a speed of 10 degrees per minute. For the cooling, the furnace did not have a cooling function, so I just left the glass panels overnight to cool naturally in the furnace, and the next day I took them out. And I also monitored the electricity consumption. The absolute values are, I think, not that relevant because it's not optimized for this process. The furnace is not optimized for the process. What's maybe interesting is that comparing the treatment at 550 degrees for 2 hours with the one at 400 degrees for 8 hours, we can see that holding the temperature at the high level for a longer duration actually needs more electricity than the higher temperature for the shorter duration. The measurement of residual stresses we did with a scalp. We also measured the geometry at different points, but we didn't notice any change at temperatures that we used here. For the residual stresses, we measured on both surfaces, so both the top and the bottom surfaces. We also didn't detect large differences there. For some samples, we also measured in different directions, so X and Y, but since we were quite far from the edge with the measurement points, this was also not, the difference were not very large. Here I would like to show the residual stress distribution. These are for the 3 series at 550 degrees, and so the one at 550 degrees and the 2 at 400 degrees. Before the treatment, so we see that we had quite high residual stresses, compressive stresses at the surface, around minus 110 megapascal. After treatment at 550 degrees, we got completely rid of the residual stresses with 550 degrees. With 400 degrees, there was a reduction. The reduction was higher with the longer holding time, but we can still see that we have a quite prominent or quite high residual stresses. If we look at the mean value, also here, it can be seen that at 550 degrees, so if we compare these with these, we got completely rid of the residual stresses. At 400 degrees, there was only this partial reduction. In the next step, I conducted a 4-point bending test. It's the test from the standard, nothing special. We measured the force and also the midspan deflection. From the force, we then calculated stresses. Since I only had 4 samples per test series, it didn't make really sense to do a statistical evaluation, but it was, I think, sufficient to compare the stresses, the reduction in bending stress that we obtained. And also here it can be seen that the reduction after treatment at 550 degrees was significant. At 400 degrees, it was in line with what we measured for the residual stresses. I would like to focus a bit more on the fracture patterns. So we can see here on the left side 2 representative fracture patterns from the fully tempered glass, so the reference series. You can see that the fragments are very small, so the degree of tempering was quite high for these glasses. It was also the failure during the test was quite explosive. The 2 examples on the right are the ones treated at 550 degrees for 2 hours, and we can observe that the fracture pattern is actually characteristic for annealed glass with the large shards and the radial distribution of the cracks. If we look now at the ones treated at 400 degrees, we can see that after 2 hours treatment, the crack pattern shows still quite small fragments. We can see a little bit the radial distribution of the cracks, but I would say it's still quite typical for fully tempered glass. After 8 hours of treatment, it already looks more like a heat-strengthened glass, maybe. So after knowing how it fails and how our crack pattern looks like, the next step for me was to see, okay, can we cut it now properly? And for that, I just use an oil glass cutter, so the easiest things that you can do in the lab, and running pliers for breaking the glass. And here is a panel before cutting, so before scoring and breaking, and afterwards. It worked pretty well. The damage that you can see here is mainly because of my poor skills in scoring. So the first scoring lines that I made, the oil glass cutter just slipped on the glass. And you can see in the corner, even after the treatment, the CE mark for the fully tempered glass is still there. So for me, this proved that basically if you want to or if you can retrieve fully tempered glass and you want to process it, to cut it to different sizes so you're able to reuse it, this can be applied. With this, I was quite fast compared to other presentations, but there will maybe leave time for questions. I come to my conclusions. Thermal treatment at 550 degrees for 2 hours allows a full relief of the stresses. It also allows to cut the panels to whatever sizes is needed afterwards. Also, the fracture pattern is characteristic to annealed glass afterwards. Treating at 400 degrees allows only a partial relief of residual stresses. With the longer duration, the reduction is higher, of course, but the fracture patterns are still typical for tempered glass, depending on the duration, either fully tempered glass or heat-strengthened glass. So for this, I didn't even try to cut them because it doesn't make sense. It will probably break. And as an outlook, in the next step, the transferability of these findings also to aged thermally tempered glass should be assessed. To be honestly, I don't see challenges there, but during the project, I was not able to get thermally tempered glass from buildings that where the facade was removed. So this we will investigate in the next step. And then also the transferability of the findings to an industrially feasible implementation. I think the main challenge is the required cooling time. So it needs to be cooled relatively slowly. And for industry, this might be only interesting if there is enough amount of glass to be processed like this. And also application of the glass panels after this residual stress relief treatment. And the ones that I cut before, you saw that the dimensions are quite strange maybe. We cut it like this to later build this kind of translucent aerogel glass bricks. These were developed by a colleague of mine from EMPA. And they are basically made of 2 layers of laminated glass with a spacer and a cavity in between filled with aerogel. So we thought in the next step we will try probably to laminate this glass and see how we can use it further. With this, I would like to thank you for your attention, and I'm looking forward to questions maybe.
Thank you very much.